In this video, I will go over the solution to motion where in the horizontal direction, the only thing that I have is an ideal spring force. So I will apply Newton's second law. F in the x direction, the x component of the net force is the mass times the x component of the acceleration, and I know that the acceleration is the second time derivative of x. I want to remind you here, when you see x dot, this really means dx over dt. Okay, the dot represents a time derivative with respect to time. When you see x double dot, what this represents is the second derivative of x with respect to time. And this is velocity, this is acceleration. Now, if the only thing that I have is an ideal spring force, I know that the x component of the net force will also be minus kx. This means that I have an ideal spring. Now, because that's the net force in the x from Newton's second law, and this is the actual net force, they have to be the same thing. So I get the equation x double dot equals minus k over m times x. Now, if I set a constant, omega squared, to be equal to k over m, then I can write this as x double dot equals minus omega squared times x. Now, this is the differential equation. This is the differential equation I have to solve in order to find how x behaves as a function of time. Okay, so I need to solve this differential equation in order to find what x is as a function of time. Now, because this is a second order differential equation, I will have solutions that have two constants. There are a number of ways that you can use to write the general solution to this differential equation. One way to write the solution is a constant times sine omega t plus another constant cosine omega t. So in this form, I'm using sine and cosine. Another way to express the solution, the general solution to this differential equation, is to use exponentials. A constant times e to the I omega t plus another constant times e to the minus I omega t. And another way to express the general solution is a constant times a cosine omega t minus delta. Now, let me circle. So I'm going to show you, this is one parameter, this is a second parameter, two constants. One constant, two constants, one constant, and this is the second constant. Okay, every general solution to the differential equation will need to have two constants. Now, why are there two constants and not three or not one? Well, we need to remember what we're doing here in terms of the physics. I am trying to find what the motion is by knowing the forces. So when I tell you that the net force is minus kx, this means that I know this. And what I'm doing here, I know the forces. I also know the physics principle that relates the forces with the motion. And what I'm doing, I'm using physics, the relationship between forces and motion, to find the motion. Now, why do I need two parameters? Well, if I know, in order to find the motion, in order to predict how the object will move, I need to know essentially two things. I need to know where the object is at t equals 0. So, for example, if the object is here, then I need to know where it is, x at 0. Not only that though, this is not sufficient. I also need to know what is the velocity of the object. This will be dx dt when t equals 0. I need to know the velocity of the object at t equals 0. So if you give me the initial position, the initial velocity, and you tell me that this object here is under the influence of an ideal spring force, then I can tell you exactly how this object will move. Okay, and these are the two constants that you need: the initial position and the initial velocity. And just so as another example, when you do a simulation with using classical physics, using molecules, in particular biological molecules is what I have in mind, you need to, when you start your simulation, you need to define the initial positions of all the atoms in your simulation, and you also need to define the initial velocities of all the atoms in the simulation. Once you have those two, and your program understands the physics, knows the physics, meaning knows the forces, then your computer can do the simulation and tell you how the atoms in the molecule will move. But you need to know both the initial positions and the initial velocities. Now I will talk a little bit more about this form of the general solution to a differential equation. We can do a little bit of algebra. I will not do that here though, but you can do it and show that, okay, this is a plus I omega t, that the constant d is really the complex conjugate of the constant c, which means the whole thing here is the complex conjugate of the first term. Now, when you take, okay, so let's say I have x plus iy, and I have the complex conjugate of that, x minus iy. When I add z with its complex conjugate, what I get, you can see, is simply 2x. But x represents the real part of the imaginary number z. So 2 times the real part of this. So I can write, due to this result, I can say that this is equal to 2 times c e, no, the real, I forgot. 2 times the real part of c e, that's my exponent, I omega t. Now I can say, I can place the 2 inside the real part, since 2 is a real number, e to the I omega t. And what I'm gonna do, I'm gonna rename, I'm gonna say c prime is equal to 2c, just to make my life a little bit more simple. Since I have 2 and c is a constant, I can just take the whole thing and rename it to another constant. And now if I say that since c prime is a constant, I can express it in this way: a, another constant, times e to the minus I delta, and then I continue to have e to the I omega t, and at the end I have the real part of a e I omega t minus delta. Now I want to show you what this means, what this represents graphically. Now, if this is the point, so if this is a to the e minus I delta, then this would be the a e I omega t minus delta. Okay, so at t equals 0, I would start, my point would start from here, and then it would move counterclockwise, so it would move in this direction, and as time goes by, the point would simply keep moving counterclockwise on the circle. Okay, that motion of the point on the circle would be the a to the e I omega t minus delta. So the point, how this point moves on the circle, would represent essentially this. Now I want to remind you, the solution for x as a function of time, I found that the solution was simply the real part of that. Now, the real part in this case is the projection to the horizontal axis. So when I have the red point moving on the circle, then I know that the projection of this red point on the horizontal axis, this is the x of t. This point moves back and forth as this is moving on the circle. This yellow dot moves back and forth on the horizontal axis, and the motion that it does is simple harmonic motion. Okay, this is a graphical illustration of what this means. The part that you have inside your imaginary number, this is represented by a dot moving on the circle, and then the solution is just the projection to the real axis. That's what I show here with a yellow dot.